Hello students, nice to meet you. My name is Gihong and I will be the instructor of this course, Language-Based Security. Today is the first class, so I'm going to introduce the details of this course, such as who I am and what I will teach and what I will expect from you guys. Okay, let's get started. Let me first introduce myself. This is my email address. And if you have any question and problem about this course, feel free to send an email. My main research area is program analysis, which will be the main topic of this course, and software security, which will be the main application of this course, and programming language, which will be the theoretical foundation of this course. You can find more details about my research at my homepage. This is my office address, and you can visit my office in office hours. In this semester, the office hours will be Monday from 10:30 to 11:30. But if you cannot make it this time, send me an email and make an appointment. The course website is here. You can see more detailed information about the course, and you can find articles and papers worth reading. In this course, two TAs will be helping you. If you have any questions, especially regarding programming assignment, feel free to post a question on the webboard in KLMS. The TAs will help you. I'm going to provide self-contained lecture slides, but I recommend you to read this book during this semester because the large part of this lecture will be based on this book. Okay, then what is this course actually about? So this course is about quite long-standing war stories, which is software bugs.
Décollage.
For a long time, software bug has been a persistent problem. As you may know, a few decades ago, we observed several very critical accidents that were caused by software bug. Here are some examples. As you can see, software bugs like floating point roundup errors, integer overflow, or miscalculation between meters and inches can cause very critical outcomes that can cause serious damage in terms of money and, more importantly, human lives. But some of you may think that, okay, I agree that this is a critical problem, but actually someone else's problem, such as government, military, or some other big companies or authorities. But unfortunately, this is not true anymore. As you can see, recently reported critical security problems can hurt yourself, such as the heartbleed error of OpenSSL, or security vulnerabilities of your smartphone can hurt your privacy, and other software errors in flight controllers or hard devices can cause more serious problem. And also, even not in such safety critical software, bugs in ordinary software we use every day also can cause a lot of cost. This is why it is really important to detect and prevent software bugs as early as possible before they are shipped. According to this IBM's report, the cost of a software bug becomes on average 100 times larger once it is shipped. So the main topic of this course is about detecting software bug in an early stage of development process. You may wonder why this problem has not yet been solved, which means why software still fails, even though so much well-designed CS education, which is much better than before, has been provided for last a few decades. One of the main reasons is that the complexity of software and software development has been a way changed and become much larger than before. Here are some evidences. These figures show that the size and complexity of modern software, such as Linux kernel or even small mobile apps. You can see the size and complexity have been rapidly growing, so that it is really hard to fully understand the behavior of such large software. The other factor is collaboration. Nowadays, almost all non-trivial software is developed in collaboration, especially in the GitHub era. You can imagine a huge amount of commits and pull requests from your teammates or even some random person. This graph shows the complexity of real-world software. This graph is a call graph of a Unix utility program called less that consists of 23 kilo lines of C code. If you take a look at this more closely, you can see how many relationships exist for a single function. In this figure, each node represents a function and edge represents the function call relationship. But please notice that there are two important things. First one is that the complexity is already very high, even though the graph only shows function level relationship, which is really abstract. The actual complexity will be far more than this if you consider more detailed information such as control flow relationship or other kinds of semantic relationships. Again, the second point, the complexity is already very high, even though this graph is from a rather small program, which is just a Linux utility. But in the real world, many programs in the wild will be much, much more complicated than this small Linux utility. So as you guess, it is highly non-trivial to understand large real-world software's behavior manually. So we really need some automated techniques. The first object of this course is teaching the principles of such techniques. So the main question that this course tries to answer is that how to formally estimate software behavior automatically before each execution. Such kind of question arises in every engineering discipline. All engineers design and implement some artifacts whose behavior is subject to the law of nature. The behavior of such artifact can be analyzed once we understand the principle of the nature. For example, mechanical engineers design and implement cars which will move following the law of nature. We humans can analyze their behavior using principles in physics. Also, electrical engineers can analyze their wireless communication devices using the principles of electromagnetism. Likewise, we software engineers want to have similar techniques that can estimate the behavior of software which is subject to computers rather than nature. The goal of this course is to understand the principle for analyzing software so that we can detect any undesired behavior in the target software. Such techniques are called static program analysis. So static program analysis is a general methodology to predict software behavior. This technique is static, which means it is done before program execution, and it is automatic, which means we are going to make a software, so-called program analyzer, that analyze other software. And it is a systematic technique, which means that it is based on a foundational theory called abstract interpretation. Static program analysis is like MRI for software in that it can scan the input program, estimate the current status of the program, and check if any possible problem exists in the program or not. So there are many applications enabled by these techniques such as bug finding or verification or traditionally code optimization in compiler. This technique is already pretty mature and many established software companies have their own product. Here are some success stories. One class of program analysis is called domain-specific verifier that targets to very specific software and very specific properties. Usually, such kinds of approaches are designed to verify the absence of software bugs in safety critical software, such as Microsoft Windows device drivers or Airbus flight controller. The other class is so-called general-purpose bug-finding tools, which targets to general software and help improve productivity of user software development process. So throughout this course, you will learn the underlying principles of these kinds of tools. The second objective of this lecture is to introduce new waves of this field and imagine what the next generation programming system would be. Definitely, the systems should significantly improve the quality of software by helping developers make safe software with simple and smart ways. Throughout the lecture, we can first imagine what the next generation program analysis look like. The second will be the new technique called program debloating that automatically simplifies large and complex software so that makes software more robust and easy to understand and easy to maintain. The last part will be program synthesis technique that automatically writes programs from high-level specifications so that it can improve robustness of software and productivity of software development. All the methodologies will be derived by a common theme, which is based on principled programming language theories combined with effective AI techniques. We are going to explore such new waves throughout this lecture. The last objective is practice and challenge. You will write program analyzers by yourself through homework and project. The goal of the homework is to implement conventional program analyzers whose design will be given. In total, there will be 5 homework. 4 of them are main homework and 1 of them will be a prerequisite. For the project, you will design and implement your own analyzer. I hope ideally you pick a good program analysis problem in your own research domain and design and implement advanced techniques with new idea. The details of the project will be announced after the midterm exam. Let me talk more about programming assignment. You will write program analyzers in OCaml using the LLVM framework, which means that you will analyze the LLVM IR code. LLVM IR is a common intermediate representation used in the LLVM compiler framework. But some of you may wonder why we use LLVM and OCaml. Let me first talk about the importance of the LLVM compiler infrastructure. LLVM is now becoming the de facto standard in CS academia and IT industry because it is really well structured and high performance compiler toolchain. It provides parser, code optimizer, linkers, loader, debugger, and so on. LLVM also has a variety of front ends so that it supports and compiles many programming languages. For example, C, C++, Objective-C, Swift, Fortran, and so on can be translated into the common LLVM IR. That is why so many large companies adopt LLVM for their internal process. All the Apple's software products are compiled with LLVM, and Google uh, is using LLVM for Chrome, and IBM recently started using LLVM also. We are going to use the OCaml language for programming assignment because it is simple, safe, and realistic and higher level programming language so that you can purely focus on the core of your homework rather than other side issues such as memory management or debugging for mysterious segmentation faults and so on. Also, there are a lot of growing demands from both academia and industry. According to the Stack Overflow Developer Survey in 2018, OCaml programmers are the second highest paid software engineers globally and third in the US. And also notice that the top most paid language F Sharp is actually Microsoft's dialect of OCaml. Homework will be managed like this. So all submissions will be managed using GitHub and GitHub Classroom. So students must have their own GitHub accounts. Here are the common workflow. For each homework, I will post a unique invitation URL at KLMS. You will visit the website and accept the homework. Once you accept, our private repository for your assignment will be created. So after that, you can push as many commits as you want before the deadline. So the final commit of your master branch only will be graded. And here are the delay policy. So we will give 80% of credit for 1 day late and 50% of credit for 2 day late. And we will not accept any submission after 2 days. Let me explain the prerequisite homework 0, which will not be graded, but I strongly recommend you try this homework to set up and get familiarized with OCaml and Git environment. It will be very simple. First, clone your repository and implement your Hello World program in OCaml. I already put some reference and tutorial in the README file of the repository. You can read and practice. But if you have any question, please post a question at KLMS. The TAs will help you. Once you finish your implementation, push it to your GitHub repository. After push, you can see your result through Travis CI. So in the future, we will provide detailed grading result through the Travis CI environment. So you have to sign in with your GitHub account. So here is a brief instruction of homework 0. As you can see, once you accept the invitation, you will have this kind of private repository. The prefix will be given and the postfix will be your ID. And then you can commit your code to the master branch once you finish your homework. And then you can visit the travisci.com webpage and see your result. I hope you enjoy all the homework throughout this course. Okay, what do you feel? Are you ready to dive deep into theory and practice of language-based security? If so, in the next lecture, we are going to start from a basic concept of programming language semantics. So see you next time.